So, hello everyone. Welcome to the TFR Colloquium. I would like to introduce Professor Navin Kashyap from IISc. He'll be telling us about the number of modes in a mixture of Gaussians with centers in a bounded interval. So, over to you, Navin.
Yep, great. Thanks a lot, Nishant, and thanks for inviting me to this to give a talk on this in this colloquium. It's a fairly, shall we say, light talk in that not much background is going to be assumed on the part of the audience, as I think is what is expected of a colloquium talk. So yeah, without further ado, let me get started. So this is joint work with my colleague Manjunath in the math department. So the title is will be explained. What exact the words in the title mean will be explained in a couple of slides. So please feel free to keep interrupt me with questions in case you have any as we go along. Like either by raising your hands, and I guess Nishant or someone, one of them can moderate on my behalf. Thanks. Okay. Yeah, so like I just wanted to put this plot up because this is the object that we will be concerning ourselves with. Like I'm assuming everybody is familiar with this. This is the univariate Gaussian. Like in particular, it's the density of a Gaussian random variable with mean 0 and variance 1. So I will refer to this expression here. The density I will refer to using the notation phi of x. But what we are concerned about here in this talk primarily is about mixtures of these univariate Gaussians. And by mixture, I mean that we take a bunch of say a certain number, need not even be finite, but like a certain number of Gaussians which are spread across, which are centered on the real line somewhere, each of them being centered on the real line somewhere. So each having center some a, so a bunch of Gaussians with centers a sub k. You're taking a mixture of those. That is, you're taking a convex combination of those densities. So in another way of putting this is that we are looking at the density of a random variable x plus z, where x is let's say a random variable with discrete support, which is supported on which has point masses at these AKs, and the weights assigned or the masses at those points is p sub k. So where x is that, and z is an independent random variable which is normally distributed with the standard normal, that is mean 0 and variance 1. All right. So I mean, so here's one such plot, like plot of such a mixture. Here it's a mixture of 3 such Gaussians. All of them. So I've put them. I have chosen the centers, all the centers to lie within the interval -2 to 2. And like so, I have a Gaussian centered at -1.99, one centered at 0, one centered at 1.99. And they're getting these weights 0.35, 0.35, and 0.3 in the middle. And if I take that, if I look at that function, the mixture density, I see that I get a shape like this. Because interestingly, there is a little saddle point here, not saddle point, but a little bump here in the middle as well. And that, so these are the type of plots that we are actually going to be interested in. Okay, so plots of these mixture densities. So the question that we're going to be addressing in this talk has to do with the modes of a Gaussian mixture. A mode is just a local maximum of the density function, okay, of the density function of that mixture. So in this plot, you can see there are 3 modes. So one at about one at about -1.5, one at 1.5, and one at 0. So this mode at 0 is actually not that easy to obtain somehow. Even though there is actually, even though I'm putting a a Gaussian here at 0 also with weight 0.3. It turns out like, I mean, only with a proper choice of weights will be actually be able to obtain a mode here at 0. Otherwise, this mode also gets killed off by the fact that the Gaussians centered at the other 2 points kind of are rapidly decreasing by the time it comes to 0, by the time you hit x equal to 0. So the question here that we are addressing is the following, that I look at an interval from -a to a is some real number. I'm looking at the closed interval from -a to a, and I require and I basically force the centers of the Gaussians all to lie within this interval from -a to a. And then I take any mixture of Gaussians whose centers lie within the interval from -a to a, and I ask what is the maximum number of modes the resulting density can have. As a function of a, what is the maximum number of modes? I mean, I'm not restricting how many Gaussians I'm putting in there. Like, well, that's, yeah, I mean, I kind of tacitly assume that it is finite, or at least, yeah, that's a finite number of Gaussians or a discrete number of Gaussians, but even that is not strictly required. Although for simplicity, I will assume that it is a discrete number of Gaussians whose mixture I'm taking. So, and like I'll right away answer this as well. So I will say that if I denote this maximum number by m of a, so what we will show is finally that like the maximum number of modes that a mixture of Gaussians with centers in -a to a, that the maximum number of modes that are possible in such a situation is it grows as a squared, it grows quadratically in a. Okay? So there are constants. So so m of a is bounded on either side by a constant times a square. So the precise value of the constants is not something that I'm going to be determining, but yeah, they're kind of within, let's say, a factor of, I mean, if you tighten the bounds that we have, they'll be within a factor of like, I don't know, 1. So C1 can be taken to be about 0.1/10, and C2 may be of the order of 10. So 1/10 a squared, between 0.1 a squared and about 10 a squared. Okay, that's, anyway, these are rough bounds, but the main important fact is that it grows quadratically in it. There's a question here, it's like.
Yes, Shrikar, you can go ahead. You don't have to raise your hand.
Yeah, so Navin, there's no dependence on number of the capital K?
No, as in no, this is because, yeah, there is no, I mean, I'm not putting any restriction at all. There is no capital, that K can be anything. So K is not restricted.
Oh, I see. So this K is now the like totally uncountable. It could, sorry, countably infinite.
Yeah, I can say it is countably infinite. It could even be, I mean, it could even have mixtures like, I mean, you could just have something like, even this is allowed, like some density already there on like, so density supported on -a to a, and density with support in support of phi is in -a to
I
a.
see, I understand. Okay.
And like a convolute, you convolve with the Gaussian.
I see. Okay.
Yeah.
Okay.
So that is also okay. Even that is fine.
Yeah. Okay. No, but I was thinking that if it was really dependent upon the, like, if capital K turns out to be very small, then order a square seems a little too much of an overkill.
Yeah. So we're not restricting T. Correct?
Yeah, I understand.
So that is a question that can be asked also, and I will touch upon it.
Okay.
Good. All right. So yeah. So I'm going to kind of turn this, like, so I'm going to push like everything else, the motivation for this problem and like everything else, I'm going to push towards the end. I'm going to turn talk on its head by not trying to say where this problem comes from. I think this problem was of intrinsic interest anyway. It's nice. It's an interesting, simple, straightforward question. It has a nice, straightforward answer, and it does take some work to get to this answer. So all of this will give us some, nice, maybe some nice mathematics involved, and I will push the motivation to the end, sort of set it in context, etc. later. So I hope you will forgive me for this. Yeah, so here's like a special case. Like if you ask for all the, so these are, mind you, these are all Gaussians of variance 1, right? And so if in the special case when all the centers I'm stuffing between -1 and 1, Okay, so I'm only allowing the centers to lie between -1 and 1, and I'm taking a mixture of Gaussians. Turns out that a mixture of any number of Gaussians with centers in -1 to 1 is actually unimodal. It has only one mode. So this is, I mean, it's a bit surprising, perhaps. One might expect that, like you place different, you ought to have, whenever you put a Gaussian somewhere, you ought to get a new bump from that, but that sometimes doesn't happen. The Gaussians are too close together. If they're kind of separated out by no more than twice the variance, then you get kind of a merging of these modes all happen. And the proof is again kind of nice. So let me just quickly go over it. I've adapted this proof from an observation that was made in this paper of Polyansky and Wu. Again, this paper I will come back to a bit later as well. So if I start with a density like this, a mixture of Gaussians, and just I make a calculation. So remember, recall that this is the density of x plus z, like x being where x is distributed like this, it's a discrete support. All it has point masses at the AKs between -a and a, and with masses at those points being p sub k. And z is an independent standard normal random variable. So I'm adding those to x plus z. And if you actually calculate this, you take just take the log of the density and take a second derivative, you can actually show that what it expresses is precisely this quantity. It is a variance -1. Variance of x given x plus z equal to little y being the argument of the derivative of the second derivative of log of x. And so it just works out like this. It's a calculation. All right. Why does it happen? I can't really say. It just so happens. It's a formula. So now, if all the centers, if all the AKs lie between -1 and 1, that means that all x is taking all its values between -1 and 1. So the variance of x is, of course, going to be upper bounded by the expected value of x squared, and x squared, whatever its conditional distribution is, whatever the distribution of x squared is, conditioned on this. All the values of x squared lie between -1 and 1, and so the expectation is also at most. Right? Oh, sorry, x squared lies between, all the values of x squared are between 0 and 1, and so the expectation is of course. So this shows, therefore, that the second derivative of log of f is non-positive. In other words, f is log concave. And so any local maximum that f can have must be a global maximum. So it can have at most one mode, and you cannot have any flat regions because these are all real analytic functions. You cannot have like a modes, like sort of uncountably infinite number of modes. You cannot have flat regions on top. So mode has to be bumped, a pure bump. You cannot have a strict maximum. Because these functions, these are all mixtures of Gaussians. Individually, every Gaussian is real analytic. If you have flat regions, that's not possible for a real analytic function. Okay, so this shows that f is unimodal. So it's a nice little observation that was made in this paper of Polyansky and Wu. So here's one example. By the way, I will say that this is a mixture of two Gaussians. It looks remarkable that even see, if you look at the center here, it looks pretty damn flat to me. This region here on top looks pretty flat, but this is still a real analytic function. So it's in fact this is not flat. It looks very, very flat, but it is still a unimodal thing. It just come kind of the mode at x equal to 0 is actually only very, very slightly higher than anywhere between -1 and 1. So this is a mixture of two Gaussians. So what happens if you take many Gaussian, different, like a lot of Gaussians? So here's an example where I take a mixture of many Gaussians. So you have to, you may not see, you have to see this here. I've blown up there's an inset here that shows the top part of this plot kind of blown up. You see these little bumps. Those are not very, so this is an incredibly flat region on top, but these are small bumps. These are very, very tiny bumps. So these got the way. So you have to be, you will get, if you want to analyze this situation here to see how many modes a mixture like this will have, a density like this will have, you have to actually be able to handle kind of variations that are quite small. We will see exactly how small these variations are going to be. So yeah, so it's a kind of a delicate analysis that one needs to be able and that one needs to carry out in order to try to capture how many modes you're able to generate in this fashion. Okay, because on top, again, it's very easy to get the plot on, like, the center part of this plot to look very, very flat. It's small little bumps which are kind of very difficult to discern from the flat, from the plot itself. You have to kind of magnify.
Navin, I have one question.
Yes.
Yes, so the constant C1 and C2 that you had in your result, the answer, does that depend on the density of X?
No.
Okay, so it's uniform for all such densities.
Correct. Yeah, these are universal constants. Yeah.
Okay, I see. Okay, thank you.
Thanks. Yeah, good question. Thanks. Right. So let's look at the upper bound to start with. So I want to say that this my number m of a, the maximum number of modes a mixture of Gaussian centers in -a to a can have, is at most a squared. Okay. So I want to say that first. So I take so here's a generic such density. So you start with very simple observations. Like, see, these centers are all between -a and a. And so each of these Gaussians themselves, each of these components within this sum of this, each of the components of this mixture already falls off when you hit the edges from beyond -a and a. Both of these, everything is falling off, everything is decreasing. Right? Any action, any maximum that must happen of this function must happen between -a and a only, because all the centers of the Gaussians are between -a and a, and all the Gaussians shortly fall off of their center. Right? Like, this is. We are looking at a really sort of, the variance is small compared to a kind of a situation. So the Gaussian variance is 1, a is kind of large. And so the Gaussians sort of fall off pretty sharply as soon as you get off the center. And so all the centers are between -a and a. Outside of a and a, then any maxima that this mixture must have must lie between -a and a. Because outside of -a to a, everything is falling. All the functions are falling. So all the modes they lie in -a to a. So that's one simple observation. Then another simple observation, and maybe a picture will sort of convey this best. So this is your picture. Like, so any modes that happen will happen like that. So let's say this is -a and a. So the falling off happens thereafter. Now, modes are local maxima. Now, again, this is a real analytic function, no flat region. So between every pair of local maxima, there'll also be a local minimum. And finally, since everything falls off, there will be, just by the fact that so there'll be basically one more maximum than minimum, because everything eventually falls off. And maxima and minimum will alternate. So finally, if I want to compute the number of maxima of this, I can take this. I can also just as well look at the derivative of f. Look at how many zeros that derivative of f has, and roughly half the number of zeros are going to be maximum. There's a ceiling here, but half the number of zeros of the derivative are going to be maximum, and the half are going to be a minimum. Okay. Maximum number of maxima is one more than the number of minimum. So the number of modes I can equate as being equal to about half the number of zeros of the derivative of this function. Right, fine. So take the derivative of this function f prime. So it's going to be of this form, where if we replace z by x. But then I extend this to a function of a single complex variable. I extend it to a holomorphic function on C, just by replacing the x variable by z. Now z is a complex variable. Now, so of course, so zeros within the interval -a to a, the zeros of the function, zeros of the derivative of the original of the mixture are going to be bounded by the number of zeros in a disk centered at a disk of radius a centered at the origin. So the question now is, now we are kind of in familiar territory. See, this is a nice holomorphic function. We are looking to bound the number of zeros of a holomorphic function within a disk. There are lots of ways of doing this. Okay, and so we pick one which you may or may not be aware of. So this comes. One can use things like Jensen's formula, or there are other such well-known techniques for counting the number of zeros of a holomorphic function. This seems to be a very powerful but yet little-known technique. I'm not sure how many of you have seen this before. So this is something that Manjunath discovered from this paper here of Ken Suze, something to do with random matrices. And but it turns out that other people are also aware of this type of result. So you're relating the number of zeros. So number of zeros of the holomorphic function within a disk, you're relating it to its maximal value on slightly larger disks. Okay, so you have 3 disks. You have a disk of radius r, another disk of radius r1, and the third disk of radius r2. Okay, so you have a disk of radius r, a disk of radius r1, a disk of radius r2, and you want to know how many zeros there are of the holomorphic function within the disk of radius r. And it turns out they can relate it by looking at the maximum. The number of zeros is related to the ratio, log of the ratio of the maximal value of the function on the disk r2 divided by the maximum value of the function on the disk r1. Okay. That ratio, log of that ratio is basically when some constant is there. There's a constant that just depends on the values of r1 and r2. So you can pick r1. Your interest is in the number of zeros within this disk r. You can pick r1 and r2 arbitrarily. So you can get so whichever this constant here you can choose to your liking. So the particular, so you can see this is kind of a very nice way of this gives us a good handle, or gives us a easy way of bounding the number of zeros within a disk. Because actually, bounding the maximum value of a holomorphic function on a disk, you can either use the maximal value theorem or the maximum modulus theorem and so on. So that that the maximum is going to occur on the boundary of the disk and so on. So things are not, this is not such hard to do. So you want to find an upper bound for the numerator there and lower bound for the denominator here to get the overall upper bound and the number of zeros of the holomorphic function within the disk R, within the disk of radius R. Not hard to do. So here in particular, what we are doing is, so we are interested in the number of zeros of our function within a disk of radius A. We take a slightly larger disk of radius A plus 1 and that doubles that radius twice A plus 1. Apply our theorem. The constant basically evaluates to something like 5. The constant that was there in front here, that evaluates to something like 5 in this case. And now we want to find like an upper bound of the numerator. So basically what we want is the maximum modulus, or the maximum value, the absolute value of the derivative function can take on a disk of radius 2a plus 1 divided by the maximum value it can take on the disk of radius a plus 1. And these are simple estimates. One can do this. I'm not going to belabor this point too much, but one simply just by completely elementary estimates, and you will get some bounds like this. So you get a maximum bound for mf prime of a plus 1, the numerator, the denominator. Sorry, I think this should have been 2a plus 1. My bad. Yeah, so the upper bound of the denominator, upper bound of the numerator, and then similarly a lower bound on the denominator. Lower bound on the denominator of this expression there. Okay, so these are just completely elementary calculations. I mean, there's absolutely nothing you're doing here. So you plug it in, and voila! I mean, that's an upper bound. Okay, it's an order of a squared upper bound. I mean, the exact constant you'll get, I think, if you put this particular values in. I think we're not trying to optimize it in any way, but here this will work out to be something like 100 a squared. Okay. So this was something that I already learned from this exercise, that there is this nice way of bounding the zeros of a holomorphic function. Counting the number of zeros of a holomorphic function within a disk. Lower bound. Okay, so this is probably where things start to heat up. So for the lower bound, again, we want to say that there are Gaussian mixtures which have that many zeros, which have that many modes. Okay, modes of the order of a squared. All the centers of the mixture must lie within a to a, within the interval from negative a to a, but it has omega a squared number of modes. So the idea here is to consider again uniformly weighted mixtures of Gaussians centered, like regularly spaced Gaussian. So these are centered at the points minus an, minus 1, etc., all the way to 0. I mean, they're just regularly spaced Gaussians between minus an and an with a spacing of a. The spacing can be chosen. We will choose the spacing really carefully, but right now at this stage, I don't have to fix a space. Okay, so I'm looking at mixtures like this. See, but like I'm only interested in finding the number of modes of such a mixture, how many modes this mixture has. So the scale factor is completely irrelevant to that question. I'm going to bump everything up or down. So I'm going to drop that scale factor. So I'm looking at now this unnormalized mixture of regularly spaced Gaussians. So when I'm going to we will compare this against the infinite series, like just a series of Gaussians, like in regularly spaced, but going on forever. This series is clearly absolutely convergent. I mean, it is uniformly convergent and so on within any interval. I mean, it has all the nice properties. It converges pointwise, uniformly in any bounded interval, etc., etc. So this infinite series is like a well-defined function. It's a continuous function on R. It is of course periodic with period a, because like the Gaussians are all kind of, I mean, just shift everything. If you shift everything by a, you're going to get the same series again. But the nice, like, okay, so this is again something that this is the major tool that we use, the Poisson summation formula. So I mean, just hopefully people have seen something like this before. At the heart of it, the Poisson summation formula is nothing but this formula here. That given a function f, okay, that given a function f, if I'm taking the sum of this, f has to be some sort of a rapidly falling function. And I look at this summation like this, summation of the function f, the values of the function at integer points, that is the same as the summation of its Fourier transform, again at integer points. This is the Poisson summation formula. So if you apply here, I'm applying it. So here we're applying it particularly the function x plus n. X is some shift of n, that's all. And so you will get shifts of, I mean, when you apply a Fourier transform to a shifted value of the argument, you will get kind of this phase factor coming into the Fourier transform. So anyway, this is if you apply the Poisson summation formula. So this summation over the integer value over integers n also becomes an summation of the Fourier transform of the same argument, and the Fourier transform of that argument. For a Gaussian, the Fourier transform is also a Gaussian for a univariate Gaussian. So the phi shape doesn't change; it just gets scaled and kind of blown. It'll get scaled up and maybe may widen out. So I mean, the Poisson summation formula is remarkable. I mean, I have in my work, which is rather applied, I found this summation formula being, I have applied this Poisson summation formula at least 3 or 4 times in completely disparate contexts, and each time it comes and gives me something mind-blowingly. I mean, it's something that just creates magic out of nothing. So here the way that we are going to use this is to try to estimate the modes of the function A. So the modes of like what we're going to be using the Poisson summation formula is to estimate the values of the function, maximum and the minimum values of the function f of this infinite series f. So it's if you just plug in x equal to 0 and x equal to a over 2 into the Poisson summation formula, you will pop out some formulas like this pop out. So these are the values of the function at x equal to 0 and x equal to a over 2. It is really not hard to convince yourself that like this function has maxima at x equal to 0, x equal to a, x equal to 2a, x equal to 3a, and so on. And minima at the half intervals, like a over 2 and 3a over 2, 5a over 2, and like odd multiples of a over 2, and even minima at odd multiples of a over 2, and maxima at even multiples of a. So it's not hard to convince yourself on this fact. With the maxima, you can, yeah, it's a sort of an exercise, if you say, if you like, in analysis. Anyway, all we require really is that like 0 is a strict maximum of FA within the interval from minus a over 2 to a over 2. This can be readily checked. And so by periodicity, NA is a strict maximum of FA within this interval. This minus a over 2 interval is shifted the requisite number of times, NA number of times. Shifted by N. The height difference between the maximum and the minimum, height difference between the maximum and the minimum, or really it is just a height difference between the value of the function at the endpoints of this interval from minus a over 2, a over 2. So there are two like endpoints of this interval and the midpoint of this interval at 0. So what is the height difference that the function fa takes? It has some height there and like a smaller height here at a over minus a over 2 and a over 2. So what is this height difference we are trying to estimate? So this, the function will look like something like that, but the height difference is what we're trying to estimate. The height difference is so the value of the function at 0 minus the value of the function at a over 2, and like simple some simple observations that shows that it is then bounded below. Completely simple bound, like you get equalities all the way, and then you throw away everything else except for the term n equal to 1 in this summation. It's a summation is over odd values of integers, and you just keep the integer n equal to 1, and that gives us a lower bound on the height. So what are we going to use this for? Here's a very simple, again, a very simple observation. See, we want to count the number of we want to try to estimate the number of modes of the function of this truncated series. Right? Like that is what our goal is. We want to sort of estimate the number of modes of this truncated series. And what we are trying to do is to estimating the number of modes of the truncated series by comparing it against this infinite series. This infinite series has infinitely many modes. But what we're trying to say is that, well, as long as you stay away from the edges of this truncation, this truncated series should also behave more or less deep inside the interior. The truncated series should behave more or less like this infinite series. The edges, like once the edge effects go away. So this gives us a way. We are trying to find a way of just comparing these two things, comparing the truncated series with the actual infinite series. So if you have a continuous function, so this is some small observation that if you take it, if you have a continuous function that differs from which is like a small perturbation of this infinite series function fa, and the small perturbation continuous, if this function g is only a small perturbation of fa in the sense that the difference between the function fa and g is at most half the height of the height function that I saw, half the height. Well, all I really require this difference to be half the height is to be at most half, to be strictly less than half the height is at those intervals, at the endpoints of the interval of this interval and at the midpoint of this interval. But it's okay. I mean, might as well ask for it everywhere. So wherever, I mean, over any interval where I have this kind of thing happening, where the difference between the values of the function fa and the perturbation g is g is a small perturbation of fa. Perturbation being small in the sense that it is the perturbation is at most strict. The amount of the value of the perturbation is strictly less than half of the original height of the function a of the function fa. So we already know that fa has a maximum in the interior of this function. It has a maximum at a over 2. Then automatically g will also have a local maximum in the same interior. It may not be exactly at a over 2. It may get shifted somewhere, but it will also be there. It will also be a local maximum there. And the reason is simply this, that what we are asking, this condition here, this small perturbation condition, simply ensures that at the center value of the function g is not ever going down below the value of the function g at the end. So this condition simply ensures the fact that the value of the function g at the center of this interval is always exceeds strictly larger than the value of the function g at the endpoint of the same interval. So therefore, g must have a local maximum in the interior. So it's a continuous function. So there is, so there is a local maximum in the interior of this interval. That's all we're asking for, because from this suffices for our purposes. Now, what we will do is, so we take G to be our truncated series, the C that like is this anormalized mixture that I had earlier of a mixture of Gaussians with centers lying in -an to an, regularly spaced Gaussians. And all we do is we show that the condition of the previous lemma holds for all the intervals an that are sort of the original mixture of Gaussians has centers in -an to an. We're looking to show that like the condition of the previous lemma that this fan is only a small perturbation of the function fa, as long as you're looking at the perturbations sort of far enough away from the edges of this interval from -an to an. So let's say it's sort of deep in the interior, -half an to an. You see that like it's on this fan function is only going to be a small perturbation of the fa function. Okay, and that is just some again, so it's just an estimates on the tail of this series. You have to get some tail estimates on these Gaussians and so on. And it's a very like completely dumb analysis here. But there's really, at best we'll be using maybe a geometric series summation formula or something like that.
Navin, could you please go back to the previous slide?
Yeah, sure.
So does it not seem to suggest that that if I have the centers of the Gaussians are at n being an element in the Z, so then I will have the maxima all like at least all there will be local maxima at every an, and in between there is a there is a dip, right?
Correct.
So it seems then the growth is linear, it seems, no?
Yeah, so
in the interval. Yeah, go on.
So that's a point. That's a good point. But like one thing is that I will come to this. Like that is true. So the number of maxima is basically going to be equal to the number of intervals in here. That is true. And the number of intervals in here is indeed, each interval is of length a. The number of intervals within here is the total length of this interval is a times n. The length of each of these subintervals is small intervals here is this size length a. Length of IAN is a. And so the number of these small intervals within here is definitely capital N. That is true.
Okay.
That is okay. But the point is I have not chosen this a yet.
Okay, so I see.
What I will do is I choose a to be about 1 over root n. If I choose a to be 1 over root n, all the Gaussians now are between negative root n to root n. All the centers are between negative root n to root n.
Okay.
But then number of modes are of the order of n.
So there has to be order square root, square.
Yeah.
I see. By this argument, can't we make it like even higher? If I choose my a to be like 1 over n third.
Yeah, then the analytical estimates fall apart.
I see. Okay.
You cannot get these kind of estimates. Yeah.
Okay.
You will not get those estimates. No.
Okay. All right.
So we know that we cannot do it because anyway, we know that we cannot do it because the upper bound is also a.
I see. Okay. One more question. So you have every time you are basically looking like unnormalized and also like some sort of a uniform choice of the centers.
Yeah.
Is that some sort of an extreme case? That this is the worst case scenario or like the best case scenario?
Seems like not really. Seems like it is pretty much anything you do, you'll get like this in modes.
I see.
It's just that like we had to happen to analyze this. It turned out that we could use the Poisson summation formula to come up with this analysis. Just so, let me just
okay, go on.
Get back to you on that. Let me just a couple of slides allow at least one more thing to say on that.
Sure.
Yeah. So that anyway completes this argument. So we have. So this shows that for all these intervals, small intervals IAN lying contained within this -half an to a half an, there is at least one maximum of this FAN function of this unnormalized mixture. And so since there are n-1 such intervals IAN within this guy here, so therefore what we have at this stage is, so I have chosen a here now. Remember, like, so what I've chosen a is this some constant over square root n. Okay, so a has been chosen to be a constant over square root n. For this last estimate to be valid. So this last estimate, to get this strictly less than half HA, I need this type of a growth rate for it. Now, so yeah, but this is it. This is like, so this gives us a construction of a mixture of Gaussians with centers in about some constant times, minus constant times square root n to constant times square root n, minus a to a, having at least n minus 1 modes, which is a squared modes. Right. So, Nishant, am I still doing okay on time, or?
You have another 10 minutes or so.
Okay, yeah, let's just, yeah, so I just want to do some related problems. Okay, let me get back to this. So, because anyway, since Shrikar brought something up. So this very closely related work, our motivation comes from an information theoretic problem, which I will come to maybe very briefly. But what the work of Polyansky and Wu, I referred to this. These were the people from whom I had adapted the proof for, when all the Gaussians we are trying to squeeze all these variance 1 Gaussians within an interval of length 2. Then you get at most one, you get exactly 1 mode, because it's a log concave function overall. So that work was motivated by a statistical problem of non-parametric maximum likelihood estimation. I'm not going to define what that problem is, but their motivation was completely different from ours. It's just that these are all, both Polyansky and Wu are also information theorists. So they are academic brothers of Rajesh and Andreessen, for example. They're like, but their motivation comes from something completely different from where we got our motivation from. But their work also basically, was done independently of ours and around the same time, maybe a few months later. So their paper came out a few months later than ours. So they showed that, the result that I claimed earlier, that you have this unimodal behavior for the mixture density when all the Gaussians are between -1 and 1, centered between -1 and 1. And they also showed the upper bound of order of a squared upper bound. Then they had this other result that gave a construction for a mixture which had again an order of a squared number of modes. But their mixture was different. Their mixture was, they started with a sinusoidal shaped density, some density that was basically take a sinusoid and shift it all the way up to make it positive. So you had basically half one, maybe if your sinusoid fluctuates between -1 and 1, shift it by 1 so that it becomes all positive. Truncate it to between -a and a and convolve with plus. Okay, and that itself turns out to have about order of a squared modes. So Shrikar, so this is another example of something which looks very different from what we started with. Ours was all uniform, but this looks rather wavy, and you still get the same number of modes.
Thank you. This is exactly what I was going to ask. Like, is there any exact example which gives you the lower bound, the precise lower bound? Yeah, thanks.
No, not really. I don't think there's any. Yeah, no.
Yeah, I understand.
I don't know what the extremum is. So this actually, so our motivation, as I said, is information theoretic. But this is a related problem that again, Shrikar, you asked at the beginning. You can ask very well. Here we are constraining the Gaussians to have their modes between -a and a. So we were looking at, we are constraining the centers to lie within some bounded region. You can remove that restriction, but only say that I only want a mixture of certain number of Gaussians, a maximum k number of Gaussians, and I want to take that mixture. This can be done in any dimension. I mean, any mixture of k d-dimensional Gaussians. And now you can ask, how should I place these Gaussians so as to get the maximum number of modes? So in one dimension, if you're trying to place all these Gaussians on a line, it is by now it's now known that you can get a mixture of k Gaussians can give you at most k modes. Okay, and of course you can get this equality because you spread these Gaussians out wide enough, far enough, you will get individual bumps at each of the locations of the Gaussians. Right. So okay, so you will always get k modes. So you can get k modes. This was shown this was shown rigorously in 2003, but it was the homoscedastic case, that is, when all the Gaussians had the same variance. That argument was given in 1981, actually using sort of the heat equation. So the heat equation can actually be used to prove something like this. Then the question was asked, or rather, then it was conjectured, therefore, that okay, you can maybe do this in any dimension if you try to put k Gaussians. you should only get K modes, but turns out that there was an example of a mixture of 3 isotropic Gaussians in 2 dimensions. You can put 3 isotropic Gaussians on the corners of an equilateral triangle, and not just get bumps at those corners, but also in the centroid of the equilateral triangle. Okay, so this is another example. This is an example of a mixture of 3 isotropic Gaussians, which gives rise to 4 modes in 2 dimensions. And in general, you can do this with simplices. Like in d-dimensional simplices, you can do the same thing. So in yeah, sorry, no, I don't know. This is not. Yeah, I guess the same trick does work for 2-dimensional simplices, but this result is saying that the mixture of, okay, so it's a mixture of even 2 Gaussians. Yeah, mixture of even 2 Gaussians in d dimensions can give rise to d plus 1 modes. This may not be isotropic, so these Gaussians may not be isotropic. They're going to be kind of, yeah, they're not. They're going. They may have. You may have to skew them to face in different directions.
Wait, Navin, D is the first index is the number of elements, and
sorry.
second index is the
yeah, I think I may have
dimension.
been screwed up. I think I have screwed up. So I think
because even if I think a square, then I'm also
I
getting
think
5.
this is. I think this is 2,
No, it is 2-dimensional and D Gaussians.
Yeah, but I think that's 2-dimensional D Gaussians in 2D. Yeah, I think that's. I think this is correct.
Believable. It is like believable if you're taking like a square, then put Gaussians on the vertices, and in the center once again you might. I mean, it seems not completely surprising if you see another pop in the middle.
Maybe, yeah. I can't remember. Sorry, I think
okay.
I'm not sure. I think I can't remember whether I screwed up on the 2, comma D or D, comma 2. I can't quite remember that. But I thought that this is 3 isotropic 2D Gaussians, 4 modes. And I think this is, I think it is 2-dimensional Gaussians is I think what this is. I think that's right.
Okay.
D 2-dimensional Gaussians. There are, again, in general, actually, there are lower bounds one can find. So there are constructions in this paper of like Amendola et al. But actually, the most surprising aspect of this is the following: there are essentially no upper bounds. This is the big thing. Provided there is an upper bound, provided you know a priori that this number is finite. So we don't even know that this number is finite. There's actually no proof that a mixture of k d-dimensional Gaussians must have a finite number of modes in higher dimensions than just 1. And there's a conjecture that actually is a Newton conjecture that actually gives an answer which is consistent with all the known answers so far, but there has been no proof of this. Okay, so very briefly, let me just touch upon how we came to this question. So our motivation was from an information theoretic problem, that of determining what is called the capacity achieving input distribution of an amplitude constrained Gaussian channel. So it's a mouthful, never mind what exactly it is. Our question is following: like, look at, we are looking at a random variable x supported within -a to a and adding Gaussian noise to it. Okay. Looking at the resulting random variable y and ask the question, what is the maximum mutual information that you can get between x and y? If you don't know what mutual information is, I have an expression here, I've given a formula for it, but this is it. So what distribution do I put on this input random variable? The only restriction on the random variable x being that it must be supported within -a to a. It gets Gaussian noise added to it, and we're asking the question, what is the distribution that I can put on x with supported within -a to a, which maximizes the mutual information between x and y, which is x plus a Gaussian, an independent Gaussian. So yeah, I mean, so there's this question was first considered by Smith in 1971. He showed firstly that there is a unique capacity achieving input distribution. That is, there is a unique input distribution that will achieve the value, the maximum there. It has various properties. Among some properties that if you there's a particular functional, which that this is kind of an optimization type of a thing that like this kind of a these are what are called these KKT type of conditions. This is a convex optimization problem. So you have these KKT Karush-Kuhn-Tucker conditions for this type of problem. You work all of those things out, you get a certain condition from which you infer the following, that the support of the optimum input of the optimal input distribution must lie in essentially the zero set of this function. There's a particular function whose zero set must contain the support of the input distribution. Okay, how this function is defined here? It is defined in a particular. It's defined through integrals, etc. It's a nice, let us say, you can make it. It's a real analytic function. We can extend it to the complex line. When you can extend it to the complex plane, etc. And indeed, by doing that, by extending this function to the complex plane and like using the identity theorem for complex analysis, Smith showed that this right-hand side has to be finite. Because this is a holomorphic function. You cannot have all of its zeros of a holomorphic. You cannot have infinite number of zeros of a holomorphic function within a bounded region, because if there's a limit point, and once you have a limit point, then the entire function must be constant. The entire function must be a zero. So that's so this was something that was shown by Smith in his analysis, that the optimal input distribution is actually finitely supported. But how many support points must it have? How many mass points must it have? That's the question we do not actually have an answer to. There are lower bounds. There's a lower bound that one can get due to a result of Shannon long back. That says that the optimal choice of this optimal number of mass points of the number of mass points in the optimal support input number of mass points of the optimal input distribution grows linearly in A, grows at least linearly in A. That much we know. This sort of falls out of the theorem of Shannon's. But there was an upper bound in this sort of recent work of Ditso et al. Come up with an upper bound, where that upper bound, if I had a few more minutes, I might try to explain it, but basically is the following. It gives an upper bound on the support of the optimal input distribution in terms of the quantity we've been studying. Twice the maximum number of modes of a mixture of Gaussians with centers between minus a. So these guys, as I said, we have this lower for the information theoretic problem. What is the number of mass points and how many mass points does the support set have? We know that it grows linearly in A, and they conjectured that. So Ditso et al. Would like to have believed that this M of A is actually order of A. So in that case, you would have gotten the support exactly. Number of support points, number of mass points in the support of this distribution is indeed of the order of A. But we showed that in fact this guy is of the order of A squared. So this only gives you an A squared upper bound, not an A. So where does the truth actually lie? It turns out that for the information theoretic problem, not the one that we have not solved, which is still open, the evidence actually strongly indicates that the number of mass points grows linearly. Not that, in fact, it's almost. This is just numerics. So these are just by brute force optimization what we get. So just to give you an idea of what the optimal input distribution looks like. Again, I cannot guarantee that this is actually the optimal input distribution. It is what MATLAB's optimization function throws out as the value of the optimizer, as what the optimizer should be. I'm not quite sure. It's a highly non-convex problem, but so this is what it seems to be. That is, the input distribution as this tries to be flat towards the center, but then it sharply rises out towards the edges. All the mass points are between minus A and B. And the corresponding output distribution, which is a mixture of Gaussian with centers here, they are it has this really kind of like something that is familiar to us from Fourier series, the kind of a ringing behavior. So yeah, so with that I can stop here, and I'm happy to take questions.
Thank you, Navin, for this wonderful talk and wonderful questions and results. So I open the floor for, maybe we should first thank Navin for the talk, I guess, and then we can follow it up with further questions. So please unmute yourself and thanks. Yes, questions for the speaker.
Can I ask?
Please go
I
ahead.
have been. So, sorry, I missed the connection in the sense like, so in the Gaussian case, you proved that it is a quadratic order. And here you are expecting, you are kind of conjecturing, seem to conjecture that it is linear order. So what is the connection? I missed that out.
So this was the connection that like this is what we have chased. This is the open problem. What is the support size of this input distribution?
Yes.
Now
but you seem to be getting that the order is a square, whereas you proved that theta a square is the in the Gaussian mixture case. So which is lower and upper.
One second. Yeah. So correct. So here, what we know here is that this is so the lower bound here is OA for this omega of A. That is at least C times A. Okay? At least a constant times A. The lower bound for this. This is known. The upper bound, we're using these methods of again complex analytic methods of Litso, is twice the number of modes of that Gaussian problem. It is this M of A is that Gaussian problem. This is an upper bound.
Yeah.
But we have shown that this upper bound is A squared and not of the order of A. So there is a gap. There's a lower bound of A and upper bound of A squared for this problem.
I see. I understand now. I understand. Basically,
conjecture. So these guys conjectured that so before we proved this, these guys conjectured that this is this. The upper and lower bounds matched. They wanted M of A. What the problem that we proved that to be A squared, they would have wanted that to be of A order of A.
I see. So which you have proved.
Then they would have got upper and lower bounds. But then we proved this. We showed that is not the case.
I see. I see. Okay. So this method or this set of inequalities is kind of too weak.
Yeah, sort of.
Where would you be losing things? I mean,
not quite. Okay, so no, actually the method is not the weak. The weak is the inequality is actually all the way fine up to here. Up to here actually is okay. It is just that like the y star that you get for the optimum y star is this guy here. It is the mixture that you get when you choose the centers to be at this optimum.
I understand.
Centers according to this guy. So, but this guy, nobody said that this is the best way of choosing centers to maximize the number of modes.
I see. Okay.
It's a different problem. So up to here, it's all fine, more or less. It's just that going from here to here, there is a gap. The number of modes that you get here is still what we believe. The number of modes that you get here is, we would expect that to be of order.
I understand. Not much better. Thank you. Thank you so much. Yeah, I totally missed this point. Sorry.
So there's another question by Amitabh. Please go ahead.
Oh, yeah. Hi, Navin. Thanks for the nice talk. Yeah. So my guess, partly tell me if this is correct or not. Instead of taking the standard Gaussian mixture, if you take all of them to have standard deviation sigma, will it just scale by that? So basically a square by sigma square. That's what I think it will be, but just wanted to check if that's correct or not.
Yeah. I mean, for the original question, yes, that is right.
Yeah, for the original question, yes, it just scales by that. Okay, and if you take now mixture which is centered at AK with sigma k, so each one has a different. Is there a simple way to see what
No.
it could turn out to be? No, there isn't really.
No, I think, yeah, so all these arguments all rely on the fact that, yeah, this is a homoscedastic mixture. The upper bounds. The upper bound
Yeah.
arguments, lower bounds are, of course, I mean, okay, yeah. I don't know if you can get, if you can get more modes by asking for variances to be different. That is not so clear. So we don't have upper bounds in that situation.
Yeah.
The upper bounds that we do have are for the situation where all the Gaussians have equal variance.
Yeah. Okay, I see. Fine. And does it? Yeah, I guess. So the dependence on pKs, I somehow missed that. How does that completely disappear from the argument? I couldn't quite see how that. Right. So it
Well, we are
all depends on
optimizing
where
for all
AKs are.
PKs. No, the PKs
Oh,
are
I guess
something
you are
that we
really
you
just
can
optimizing
choose.
for all PKs. Yeah. Okay.
Yeah,
Okay.
you choose. You have the freedom to choose.
You're
the PKs.
choosing. Okay. Yeah. Fine. Okay. Fine. Yeah. Okay. Thanks.
So did you do any numerical simulation for the heteroscedastic case, like some just to see, have some fun?
I don't think I have. I'm not sure. I don't think I have. I should do that. Yeah. No, I don't think I have. It's not, but it's not really, what can I say? What can you see? What will you obtain? See, these fellows
I don't know.
simulated
I mean,
to
lower bound, I understand, like one can expect, okay, but
no, what would you get? Because you can't really do much. See, these guys simulated to Descartes' content, and then they
no,
determined
I'm not talking about
is,
I'm not talking about the
is
analytical result. Just to have maybe some surprise pops up somewhere. Like
no,
if you have
my point is this, no, the point was this. What I'm trying to say is that, see, despite simulating, etc., so Ditso et al., they conjectured, they still hard in they wanted this to be true. Their simulations, etc., may have shown something, I don't know, but their simulations seem to be consistent with this fact. Because what I guess, maybe you can't, this is a tough optimization problem. If you try to optimize because you're optimizing for a fixed value of A, if you fix the number of centers, right? If you fix the number of centers, it's a convex problem. Where to place those centers to kind of get the number of districts. So that can be, I think that is probably a convex problem. But like here, you're not, so here it's a little, here you're allowing, you can place as many centers as you want. So you have to kind of, you have a bunch of different optimization problems. So number of centers is equal to 10, 20, so on. Like, you have to keep increasing the number of centers till you get to the maximum value. So when when your intervals get larger and larger, this kind of becomes very, it's harder and harder to do, to optimize, because the number of choices gets much kind of, MATLAB, for example, will be able to handle, so the table that I have put up here, the edges, these points I will start to not believe, whereas up to A about 20, 25, okay, these plots are probably okay. That is, these are probably the right values for the optimizers. But beyond this, I don't know. It gives me an idea for like equal covariance case. But yeah, if you also throw in an extra, maybe with heteroscedastic, but I'll have to also choose the variances. That's a huge number of degrees of freedom. I don't, yeah, it could, I'm sure I won't be able to optimize, but you're right, I might be able to find some interesting around that.
Nice talk. Thank you.
Are there further questions from the audience? Let's thank the speaker again.
Thanks.
Thank you, Navin. Thank you. It was very wonderful talk.
Yeah, thanks, Rico.